Hello, good morning. How are y'all doing today? Oddly, my something is not right with my audio, and I can't hear you if you're talking. Oh yeah, no audio again, huh? All right. Let me try to fix that. I don't know why it's not working. This was very reliable last semester, and this semester is not working so well. So let me try disconnecting something here. But see, this is what fixed it last time. Disconnecting this. Reconnecting it. Huh. And it was all working yesterday. Oh, this is so annoying. Here, I'm also going to shut off the mixer and turn it back on again. Did that do it? Oh, I need to reconnect here. Mm-hmm. Oh my goodness. Okay. Did that do it? No. How weird. So you can't hear anything, right? Well, this is all, this happened 2 days ago, didn't it, right? Oh, let me do this. Let's see. Oh, we got something, I think. Can you hear me now? No. Can you hear me now? So I think you guys are trying to talk because I can see something on my meters going, but I can't hear you. Anything now? Oh. Can you hear me clearly, or could you hear me kind of echoey? There, let me turn this off. Okay, so now you can hear me, but it's coming through my internal computer microphone, not through the usual microphone. Oh, gosh. This is something I definitely have to work on. I thought I had fixed it 2 days ago, but apparently not. All right, so this is not working. So now I'm going to try. So I reset the mixer, and now I'm going to try disconnecting the USB again. And reconnecting it. And do we have anything? Oh, now we got something. All right. Okay, that's really annoying. That's what I have to do. I think I'm gonna have to reboot my whole system in order to get it going again. Okay, now you can hear me good, right? Yep.
Yes.
Yep, you're nodding. All right. I didn't work on this problem over the last 2 days because I figured last time we got it fixed. And this time, I just went through all the same steps I did last time. I just did it faster, right? I rebooted my mixer. I disconnected the USB, reconnected it, and, well, actually, first thing I did was I just disconnected the USB because that seemed to fix it last time. And then reconnected it, and then that didn't work. So then I rebooted the mixer, and that didn't work. So then I rebooted it and disconnected the USB, and that seemed to work. But why this is suddenly failing after a year of it working perfectly, I don't know. So glad we got that fixed, at least for now. All right, so today is Thursday, January 27th, the C programming course. How are y'all doing today? I couldn't hear you before, so I'll have to ask you again. How are you doing today?
Doing good.
All
Doing
right.
well, thanks.
Good. Is your first week off to a good start?
So far, so good.
Yeah, mine was.
How many of you had on-ground courses that suddenly went online?
I did.
Oh,
It's my IT class.
kind of a bummer, huh? Are they planning on returning in a couple of weeks?
2 weeks, hopefully right now.
Okay,
But we'll see.
we'll see, huh? Computer science got a permission to just stay completely online without going on ground. So whereas most departments now have a requirement that at least the full-time instructors have to teach at least half their courses on ground, the dean looked at our courses and went, "You guys are doing great online. You know, your success rates are up, your enrollment rates are up. Some students do want some on-ground classes, so we're offering a few of those, but for the most part, we're still staying online, and we probably will for the foreseeable future. We will slowly start to introduce more on-ground courses, but our online ones are just going gangbusters. Whereas the rest of the college is seeing a decline in enrollment overall. We're down by about 10% from a year and a half ago. Computer science is still doing pretty well. So we're going to stay the course as we are, and which means I'm just going to continue doing these courses the way I have been, which is today going on Zoom and YouTube and just doing these things live. So if it works for you, it works for me. Oh, so what do we got going on today? So today we are going to start writing our first C programs. I showed you a little bit last time, but they weren't really complicated. They weren't any more than just printing out some things and getting some input from the user. So we'll kind of do that again. Plus, I'm going to show you how to log in and set up your development environment and start writing your own C programs. So let's get started. Any questions before we begin? No, don't hear any. All right. So a couple of the basics about the C programming language. It's very similar to Java. In fact, if you kind of look at a C program and a Java program and you step back a little bit, blur your eyes, they look very similar. They got a lot of the same syntactic constructs, but here's some of the differences between them. We went over some of the differences last time. I'll go over some of those again, but some of the key differences are, first of all, no public and private stuff, no classes. So some people think of C as being kind of like Java, but without the classes and without the public and private stuff. However, the opposite is actually true. It's Java is basically C with the public and private and the classes stuff added on. Another big difference is that variables and functions must be declared before they are used. And function is the C word for a method. In Java, we call them methods. In C, they're called functions. Basically the same thing. But the key difference here is that you have to write your programs from the top down. If you're going to call a function in one part of your program, you must have pre-declared it or predefined it in another part of the program up above. Same thing for variables. If you're going to use a variable, you have to make sure that variable has been declared up above. And the reason for that is the C compiler is what's called a one-pass compiler. It takes one pass through your program, and that means it has to know the names of things before those things can be used. Java compilers are a two-pass compiler, meaning it makes one pass through your program to learn the names of things, and then it makes another pass through your program to actually translate it into the Java bytecode. So a two-pass compiler for Java, but only a one-pass compiler for C. And that means you have this requirement that things have to be declared before you use them. We went over this last time. In Java, you've got the int data type, which is declared to be or defined to be 32 bits. And in C, you also have int, but the size of it is processor dependent. Now, on the processor that we're using, they are in fact 32 bits, so they do match. Java has float. C also has float. Java has double. So does C. Java has Boolean. C has no direct equivalent. What do we use for Booleans if we don't have them in C? I'm asking you a question.
Int.
Yep. Or you can actually use character, or you can use any other of the numeric types. 0 equals false. Anything else is treated as true. Java has the character type, but it's a variable size. It can be anywhere from 1 byte up to 5 or 6 bytes. That means that C has no direct equivalent. Java has the byte type, and C has the char type, and so that's the closest thing that C has to a byte. And then finally, Java has string. C uses a character array for that. So the type would be char bracket bracket, or later on in the semester we'll see it represented as char star. So a little bit about strings, in particular what are called string literals. A literal is a value that is written in your program directly. So if in my program I write the number 35, that's called a literal value. It's literally there. The opposite of literal would be a variable. So if I set a variable x equals 35 and then I use the variable x within my program, that's not a literal value. So literals are basically constants, and they are written directly in your program. So you're already familiar with doing numeric constants in your programs. You did that in your previous courses. I just want to tell you a little bit about string literals. And it's basically the same as it is in Java. If I put a character inside of single quotes, That is not a string. That is just a single character. If I put a string inside of double quotes, that is a proper string. It's actually an array of characters. And I bring this up because what you cannot do is you cannot put a string, a multi-character string, inside of single quotes. It will actually give you an error. So when you're writing string literals in your program, put them inside of double quotes. If you just want to put a character literal in your program, it goes inside single quotes. The operators in Java and C are very similar. You've got your basic arithmetic operators like plus, minus, times, divide. You've also got the modulo operator. It's the same as it is in Java. You got your increment and decrement operators. Those are also the same as in Java. Plus plus can be used to increment, minus minus for decrementing. You can also use plus equals, minus equals, times equals, divide equals, modulo equals. This is also the same as in Java. Equals is used for assignment. If you want to do equality, like if something is equal to something else, then you have to use the double equals. So again, that's also the same. Got and, or, not. The array notation is the same using the brackets. And then Java and C both have these operators which you probably never used in a previous course. These are called the bitwise operators. And they are used for doing things like shifting bits around within an integer. So you can move bits to the left, you can move bits to the right, you can isolate or mask out bits, you can set and clear certain bits, and you can do that with these operators. But those are all exactly the same as in Java. Your flow control statements like if, while, do while, and for are also exactly the same as in Java, so no changes there. Well, the syntax of them is the same. You still do an if the same way, you do a while the same way, do while is done the same way, and a for is done the same way. The big difference here is that what goes inside the parentheses in Java, that would be a Boolean. You would have to put something there that is true or false. But in C, all you have to do is put in something there that is numeric, because we're using integers for our placeholders or our stand-ins for Boolean values. So anything that evaluates to a numeric value can be put inside of the condition. 0 is false, anything else is true. C also has the switch, just like in Java. It works the same way. You've got to put in those breaks in order to make it fall out of the switch. One difference between C and Java is that in more recent versions of Java, you can do a case using strings. So you can do string comparisons in Java. You cannot do that in C. In C, they are strictly numeric or characters. So you can't do string comparisons. Are we doing okay? So last time, we did a little bit of outputting to the screen using the printf function. we were using it to display a prompt to the user and also to display numeric results from a computation. If you remember, we put in quotes something like, enter your age. So the printf function in C is very similar to the system.out.printf function in Java. I don't know if you ever used that in your previous courses, but the functionality is almost identical. So if you just want to print out a string, this is how you do it. Just put it in quotes. If you want to print out a number, then you also use printf. Except that you put in something here called a format string. And then you follow that format string with some variables or expressions that you want to insert into that string. For example, if I want to print, hello, you are, so many years old, then my format would be hello, comma, and maybe a string for the person's name. And then you are, and then another placeholder for how old they are. This is what the printf statement would look like. So we got the name printf, we got our format string, which contains all the characters that we want the string to output, plus these placeholders for where we're going to insert the values of variables. So the way the printf function works, kind of behind the scenes, is the printf function is going to start with your format string, and it's going to work through it from left to right. So every time it encounters just a normal character, it just outputs that to the screen. So it sends an H, and then an E, L, L, O, comma, and a space. When it encounters this percent sign, it kind of stops and goes, oh, that is a placeholder for a variable. So it looks at the next character to see what type of thing it is. In this case, it's a string. So it knows it's going to be outputting a string, and then it goes and it looks at the first variable listed after the format string. And so this one is going to go where that placeholder is. So printf is going to go look up the value of the variable, output the characters from that variable because it's a string, and then once it has finished with that string, it's going to resume outputting characters from the format. So it's going to go comma, space, YOU, space, ARE, space, and then here's another placeholder. So then it looks at the next variable listed, and it puts that one there. And then it picks up where it left off, and it goes to the end of the string, and then it's done. So it's just working from left to right, and every time it encounters a placeholder, it goes and it looks up the corresponding variable listed after the format string and inserts its value in that placeholder. So I'm going to say what you might be thinking here, which is the order of the format placeholders is the same as the order of the variables listed after the format string. So whatever order the placeholders are in, the variables need to be in the same order. Would you need the ampersand for this? No. The ampersand is only used with Scanf, and we'll get to that on the next slide. Is there a cap on how many variables that can be used? No. At least not a practical one. The placeholders, there's a great variety of them you can use. I'm going to go over a few of them, the ones you're going to need for the next couple of assignments. We've already seen %s, which stands for string, %d, which stands for a decimal integer, decimal meaning base 10. %f for float, and %lf for double. And you may be wondering, why isn't d just used for double? Well, it's already used for integer, base 10 integer, and then you may follow that up with, why won't we just use %i for integer? And in fact, you also can use %i for integer. So %i and %d also work, or they both work. The reason why LF is used for doubles is because in the original versions of C, there wasn't a double data type. There were long floats. Long just means that it uses double the space that a float does. So a float might take up, let's say, 4 bytes of storage, and a double would take up 8 bytes of storage. So there were short floats, and there were long floats. So that's why LF is used for doubles. For the float data types, like float and long float, you can also do things like %.2f or %.2lf, and that means it's going to round the floating point number to 2 decimal places. Okay, so %, and then a decimal point, and the number of digits you want after the decimal point, and then an f, it means round to 2 decimal places. And you can do like %.2lf, and it will do the same thing for doubles. So if you go look up the documentation for Printf, you'll find all the different format placeholders that you can use. There's maybe a dozen or so that you can use. But these are the ones that you need for the assignments we're doing this week. And by the way, if you have a question, for those of you on Zoom, you can either post it on the chat, and then when I happen to glance at it, I'll answer your question, or you can just speak up anytime. Okay, Scanf works very similarly to Printf. You've got a format string at the beginning, and then some variables that you want to put your input into in the end, listed afterwards. So you start with scanf, and the F here stands for formatted. So you're scanning through the user's input, and you're applying a specific format to it. So you're trying to see whether the user's input matches the format that you showed. So you're basically painting a picture of what you want their input to look like, and if it matches that picture, then it will assign the values to the variables. So you put in here a format string. In this case, I'm saying I want the user to type in a base 10 integer, and then if they do, it will put it into the variable you have listed after the format string. And for scanf, you have to put an ampersand in front of the variable name if it is one of the primitive types, like integer, character, double, float, and so forth. If it's a string, then you're not going to put an ampersand on there, but we're not going to be inputting strings just yet. So for now, the recipe is if you're going to put an ampersand in front of the variable name in your scanfs. Later on, in a few weeks, we'll start learning about why you would want to leave the ampersand off and why you would want to put it on there, but for now, you're just going to put it on there. If the user's input does not match the format, so if you said to input an integer and the user types in a string, then the variable simply just does not get assigned. So it will leave the value of this variable untouched. You can get input for multiple variables at the same time. You just put multiple placeholders in your format string, and then you list out both the variables with commas in between, ampersands in the front, and it will assign each one of those in turn as it scans through the user's input. How does Scanf know the difference between one number and the next number? Well, the user has to put in some kind of separator between the two numbers, and typically it's white space. White space are things like spaces, tabs. They can even hit the enter key on the keyboard. So as long as the two numbers are separated by a gap of some sort, then Scanf will know that the first number is done and the second number is picking up. Okay, so even though there's no space in between the two placeholders, Scanf is still looking for a space of some sort to know where one number ends and the next one begins. Okay? Are we good? Yeah, we got a thumbs up, got a nod. Someone on the YouTube chat said, every time I see printf, I'm quickly reminded of how great string interpolation is. Hopefully Java brings something like string interpolation into the language. Do you mean by that the ability to insert variables directly into the string, kind of the way that C is doing it? I think that's what you mean. So Java does have system.out.printf, which works just like the C's printf, and so that may be one workaround that you're looking for. But it is kind of annoying that if you want to just use system.out.print or system.out.println, you do have to kind of like assemble the string yourself. You have to put the first part of the string in quotes and then use, the plus operator, and join that to the variable, and then plus again, and then join that to another string. And it gets really ugly and really tedious after a while. So yeah, I'm with you there that it's not the best thing. However, printf does have kind of that little learning curve to be able to put in those placeholders. I kind of like the way that a language like Perl or the Bash shell does it, where you just put your string in there and then you just put $signs in front of the variable names, and it just goes and looks up the value of the variable and just sticks it right in there. That's really clean. You just all you have to do is put a $sign in front of a variable name, and it knows to put the value of the variable right there. No other questions? Oh, I'm reminded here that in C# you can do the $sign thing in front of the variable names, and it will put the variables directly in there. And then Python almost kind of has something like string interpolation. I think you just put %signs in the string, and then you can list them afterwards, kind of like printf does. Except in Python, you don't have to tell it the types. It just figures it out. Okay, really quickly here, the basic structure of a C program. At the top, you're going to put this. Now, I call this the pound sign because I'm old school, but these days I guess you call it hash or hashtag. The proper name for this is octothorpe, but no one calls it that. So you'll hear me say pound include, but other will now say just hash include. And then in angle brackets, you put this stdio.h. And so this is kind of like an import statement in Java, but it's actually different. But Java programmers tend to think this looks like an import. But what this is doing is it is letting the compiler know about all the functions that can be used for standard input and output. Standard input and output are things like opening and closing files and printing things to the screen and getting input from the keyboard. So all the kind of standard input-output stuff that your program typically needs to do. Then you've got your declaration of the main function. And in C, it's simpler than it is in Java. It's just simply int, and then main, and then 2 parentheses. Later on in the semester, we'll see a variant on this that looks a little bit more like the Java one, which includes that args stuff in the middle. But for now, it's just int, main, and then 2 parentheses. So it's a lot simpler than it was in Java. And then finally, between the curly braces, you just list out the statements that go in your program. And then that's it. So let me give you some names for these things. This is called a preprocessor directive. So these are not actually C statements. These are for a different thing called the preprocessor, and they start with this octothorpe, the hashtag or the pound sign. If you do have any global variables, they're going to go here in between the preprocessor directives and the functions. And then it's followed by your functions. So start with your preprocessor directives. You may have more than one. Followed that by your global constants and variables, and then follow that by your functions. And then remember, you have to declare them from the top down. So if you're going to use a global variable somewhere in your program, you need to declare it up at the top. If you're going to have multiple functions in your program, make sure you declare the functions that you're going to use before you actually use them. So I'm sure as we go through the session today, you will probably have some questions. I intentionally kind of blast through this material and not show you every last little detail about what it does and how it works, so that there will be questions later on. So I think what we'll do today is I'll start showing you how to log into your environment, how to write your first programs. And then again, if you have any questions, just ask them. Either post them in the chat or just speak up, and then we'll answer them. So when you log into your development environment, and for those of you who are in my class, this is the address you need to go to, thea.cs.sierracollege.edu. It will prompt you to enter your student username and password. And if you're doing also the multi-factor authentication, it'll ask you to, do the little check on your phone. And then once you pass all of that, you will be presented with this page. Now, the reason why it looks so bare bones is because this was developed by myself and a couple of students. We took the Theia programming environment, which is a third-party open source project done by other people at the Eclipse Foundation, but it by itself isn't a complete environment. All it is basically is just the editor and the file browser. Things like an environment where you can actually compile and run programs, that's all external to the Theia environment. And so what myself and the students did was we took the Theia environment and then we wrapped around it the shell that's needed to actually compile and run your programs. So there is a central server. It's a Linux machine with like 8 gigabytes of memory and plenty of storage space. And then when you launch your environment, it spins up a little virtual machine. So you get a little virtual Linux environment just for you, which has, I think, a gigabyte of memory and access to some storage space. And then it runs the Theia environment on top of that. So you've got Theia sitting at the top of that. Underneath is a Linux virtual machine. And then underneath that is the actual host machine itself. So that means that when you're running the environment, you're sharing it with other people. There's not only our class that's using this, there's also the C++ class that's using this as well. So there could be up to 30 or 40 students using this simultaneously, but on a typical day-to-day moment, there's probably no more than about 5 or 6 people using it at any one time. So the reason why, again, this looks pretty bare bones is, well, we're computer science students, we're not graphical designers, and so it doesn't look that pretty. So what you'll see is a little welcome message, and then you'll probably just have a single button here that says Launch Computer Science 46. Now I see both here because I'm faculty and I can see both environments, but yours probably just says Launch Computer Science 46. So you'll click on that button. Oh, I probably need to log in again. Let me do that. It's been a while since I used this. A while meaning like more than half an hour. And then it will launch your programming environment. And this is what we had last time. So over here in the top right hand corner is your file editor. On the left hand side is a file browser. And down at the bottom is the command line where we compile and run your programs. So let's go ahead and just do a very simple program to start with. Let me close out these tabs just so we can kind of reset things. I'm going to go File, New File, and let's give it a name. Let's call it like hello.c. So your C programs have to have the extension .c on them. And then we'll start out with our very simple program structure. We'll start out with that preprocessor directive, the include, and then we'll go into our main. And let's just have it print out the word hello. That's all. Before you compile your program, you need to save it. You can just do File, Save, or you can use your keyboard shortcut. On the Mac, it's Command-S, that little propeller symbol. On Windows, it's going to be Control-S. So I'm going to manually select Save, but in the future, I will probably just use the keyboard shortcut because it's faster. You can tell if your file has been saved or has not been saved by the tab up here. If you look here, it's got an X. If I make a change to my program and I don't save it, let's say I change this to just a period, This changes to a dot. See how it changes to a dot there? That means that your file has not been saved yet. As soon as I save it, I'm going to go Command S. You'll see it changes to an X. So if your file has not been saved, then when you try to compile it, you'll either be compiling an empty file, or you'll be compiling the last version of the file since the last time you did a save. With my program now saved, I'm now going to compile it. So the way you compile it is you type in the name of the compiler, and then you follow it by the file that you want to compile. So the name of our compiler is called Clang, C-L-A-N-G, and then hello.c, and press enter. What happened? Did it work? So in a Linux environment, if it compiled successfully, you will not get a message. It will not say, success, you've compiled the program. It just simply returns the prompt back to you. So maybe a way to state that is, no news is good news. If you did get an error, it would then display that error message in the command line area. But we didn't get an error, so now we're going to run it. And to run it, we do // and the name of the executable, which is up here, a.out. Press enter. It says hello. Good job. We did it. So hopefully you're able to kind of follow along. Maybe you've got Zoom over in one corner of your screen, and then you've got Thea set up, and you can actually just type things in as we're talking and try to follow along. Maybe we could have this program prompt the user to enter a number, and then it will say hello that number of times. Let's go ahead and have it print out a prompt like how many times to greet you? And then we'll have them type in a number. So we're going to need to do two things. One is we're going to need to declare a variable, and then we're going to use the scanf function to get input from the user. So let's go int, let's call it num, and then scanf, %d, comma, ampersand num, semicolon. And then finally, we want it to print out hello that number of times. So we're going to need a loop to do that. Let's use our good old for loop for int I equals 0. I is less than num, I plus plus. And then inside the curly braces, we'll just print out hello. What do I need to do next?
Save.
Save it. Very good. So I can do file save, or I can just do Command S or Control S. What's next?
Compile.
Compile. Very good. So I'll type clang, hello.c, press enter. No news is good news. So now I'm ready to run it. /a.out, just like before. How many times to greet you? Let's say 5. Did we get 5 of them out of here? Let me scroll. Let me make this pane a little bit bigger, and we'll count them. 1, 2, 3, 4, 5. Looks good. Last time, we started digging into what does it look like if you make an error. Why don't we try some of that stuff? What would be some common errors that you might make here?
Get the ampersand.
Forget the ampersand. All right, let's take that off. I'm going to save it, and we'll do a compile again. So this error message is a little obscure, but once you recognize it, you'll know what it's asking for. It says, the format specifies type of int star, but the argument has type int. And then it points to these two things here. So when you see this message, basically it means you forgot to put the ampersand on there. What else could we do? What else would be some common error messages you might make? Not common error messages. Common errors.
Forget the int in front of the I.
Okay, let's take that off. Use of undeclared identifier. Identifier is just compiler speak for the name of something. In this case, it's a variable. So it says use of undeclared variable called I. So it's pointing at this one, and this one, and this one, saying that there are 3 places where we used I, but we didn't declare I to begin with. We didn't tell it about this variable called I. So we could either just put the int back there, and alternatively we can insert int I on the line above, and both of those will work just fine. What would happen if we didn't put the new line character on here for the hello? What's the output going to look like?
It's going to be a string of hellos.
So it's just going to go like across the screen.
Yep.
Yep, because that \n tells the cursor to go to the next line. And without that, it just stays on the same line. Notice also that my prompt immediately followed the period. It itself didn't even go on the next line. So when your program ends and there isn't the new line character sitting at the end of the string, then your prompt, your shell prompt, is just going to go right after that. Let's try this. Now I have a correct program. What if I type in something that's not a number? Let's type in the word 5. What happened there?
I would think num was never initialized, so it probably remains 0.
Yeah. So what happened here was this when it encountered this word 5, it didn't recognize that as a number. We were expecting it to be a decimal number, and so this value for the variable called num never got assigned, and its value just stayed the same. So actually, here's another difference between Java and C. I forgot to mention that way back on one of the first slides here. So let me just, I'm going to put a new slide right after this one.
Professor Brown?
Yeah.
Quick question. You said num stayed what it was.
Right.
The question is, what was it?
Oh, so that's what I was just going to get to here.
Ah, okay.
Okay, so in C, variables do not get a default value. So if you declare a variable like int x semicolon, then all that C does is it just sets aside memory for this variable called x, but it does not put a value in there. So if I was to print out the value of x without assigning to it, I would just get whatever happened to be in the memory to begin with. So it might be a 0. It might also be just some random value left over by some program that ran in the past. So when you declare a variable, all C does, all the compiler does, is just sets aside a little chunk of memory for that variable, but it does not put a value in there. We call this a garbage value because we don't know what it's going to be. It could be a 0, it could be like 100, it could be like -2 million. We don't know. And the value that's in there could actually differ as we run the program more times. Contrast that with Java. In Java, when you declare a variable, it will automatically initialize it to be 0, or false if it's a Boolean, or null if it's an object. So this is an important thing to remember. In C, variables are not initialized. Now, it so happens that in the program that we wrote here, the value that was in num happened to be 0, and so it just simply didn't print anything out. But it could have been like 100, and then we would have gotten 100 hellos, and we wouldn't know why. If I run this program again, I'm going to guess it still behaves pretty similarly, but we might at some point run the program and discover that it has some junky value in there. So what a lot of programmers do is just go ahead and explicitly initialize the variable. Now, in this case, we don't really have to do it. You know, we're initializing a variable and then following it by a scanf, and as long as the user types in a number, its value will be overwritten. So maybe this kind of leads to another question, is why doesn't C initialize variables to begin with? Why does it just leave them as whatever value happened to be in memory? Any ideas why C doesn't do that? Well, the answer is pretty historical. Remember, C is a very old language. Dates back from the 1970s. What were computers like back in the 1970s?
Huge.
All right, big computers.
Used vacuum tubes.
Well, yeah, maybe. The vacuum tubes were actually like from the 40s and the 50s, but 70s they were still pretty big. And so a typical computer would have been about the size of like a washing machine today.
Punch cards?
Yeah, might have used punch cards. Might have used something called a teletype for input and output. We'll get to that in a moment here. But another key characteristic of the computers back then was they weren't very fast and they didn't have very much memory. And so one of the design characteristics of C was to kind of eke out as much speed as you possibly could out of the computer. And if that meant don't initialize the variables, don't spend the couple of cycles it needs to take to put the number 0 into an integer, then don't do it. Leave it up to the programmer to initialize variables if they need to be initialized, and leave it up to the programmer to not initialize them if they don't need to be initialized. So C kind of leaves it up to you to be responsible for writing good programs. You'll find that there are a lot of places when you compile your program where C will issue what's called a warning. There are basically two kinds of error messages you can get from the C compiler. You can get errors, which means there was a serious problem with your program and it could not be successfully compiled. Those would be things like you left off a semicolon, or you didn't construct a for loop correctly, like you don't have all the pieces to it. So those are major errors, and the compiler cannot successfully compile it into a working program. But then there are also what are called warnings, which are not really errors, but the compiler flags it and says, this looks a little suspicious, looks a little sus to me, but you're in control, you're the programmer, so I'll let that slide. Those could be things like you've declared a variable to be an integer, but you're assigning a float to it, like int x equals 3.5. It'll say, that's a little suspicious, a little dodgy. Why would you want to put a floating point number into an integer? But, it'll work. It'll just truncate off the 0.5 and make it 3. And it'll let you know. It'll issue a warning that says, warning, you could possibly lose some precision in this assignment. But it'll let it go. There are many other places where you might have warnings like that. The compiler says, this looks dodgy, but you're the programmer. I assume you know what you're doing. I'll let that go. Now, things like uninitialized variables don't get flagged because that's sort of been a hallmark of the C language since the early days. So it's going to be up to you to remember to initialize a variable. You can actually turn on a compiler message to give you those kinds of warnings. Let me try it here. I'm going to remove that initialization of num, and then I'm going to compile it, but I'm going to pass in -w all, which means generate all possible warnings. Oh, and my experiment did not work. I was expecting actually to flag that as being a possible thing that looks a little dodgy, but it didn't do it. So that didn't work. But this can actually be a useful thing. If you pass in this -w all, looks like wall, flag to the compiler, then it will generate more warnings than it usually does. Let's try this. I'm actually going to comment out this scanf. And let's see now what happens. Here we go. So we got a warning. It says, warning, the variable num is uninitialized when used here. So we declared the variable num, and then we immediately used it without assigning it a value. And the compiler said, that looks a little suspicious. You're declaring a variable. It might have a garbage value in it, but you're in control. I assume you know what you're doing. I'll let that go. So we've got a working program. It compiled it successfully, but it's just probably not going to do what we wanted it to do. Gives you a little note here. It says, you might want to initialize the variable. Here's how you could do it. Add on this. So because we put this scanf here, the compiler now knows the value of num is going to get assigned, assuming we type in a correct value. And then we know that the loop will successfully run. Any other questions? All right, so let's take a look at some of the assignments that we're working on this week. So hopefully by now you've had a chance to work through the introduction discussion, case against grades discussion. You've also done your syllabus quiz. Remember to, by Friday, have made those initial postings, and then by Monday, do some follow-ups on a couple of your classmates. And I would also like you to go back, maybe even a day after that, and see if people have responded to your postings. I've noticed a lot of places where some of your classmates have responded to your postings, and it would be nice if you could go back and kind of close the loop on that discussion and maybe answer the questions they have. Like there were some people that might have said, like, over the break, I went to Hawaii, and then someone responded and say, hey, I've been to Hawaii too. Where did you go? And then there's no response to that. So go back and see if people responded to you and respond to them. So here we are in the first module. We're getting started with C. I've showed you how to set up the Theia environment. So it's just as simple as logging into the environment and getting it up and going. And then we also wrote our hello program. So this is a video about how to essentially do what I just showed you to do. And one of the purposes of writing a hello program like that is to kind of just let you know that things are working okay. The editor's working, you can save files, you can compile them, you can run them, you can get output to the screen. We also modified the program to get input from the user, so we know that we can do that. So just with a very simple program like that, you kind of like gain confidence that the compiler and the development environment are going to work the way you want them to work. That you're going to be able to output things to the screen and get input from the user. So even though these programs aren't necessarily that like practical, useful, they do serve a good purpose in letting you know that things are working. There's also a page here to read about how to submit programs and get feedback on them. But here we are. We're in this warm-up section. Okay, so warm-up programs are going to be short little programs, maybe no more than 10 to 20 lines long, really to just exercise a particular concept. So we might learn something during these class sessions, or you might learn something in the book, and then I'll have some warm-up exercises for you that are really short little programs just to practice that one particular little concept, like write a loop or do a calculation. And then I will also usually have what I call a level up program. This is a more complex program that puts together the concepts that you've learned and checks to see whether you now understand how all these concepts fit together, and then you'll be prepared now to go on to the next module, the next chapter in the book, if you will. So I've got warm-up assignments and level up assignments. Now we're doing the ungrading process on all of these, so the level ups are not worth any more than the warm-ups are. They're also not worth any less. They're either complete or incomplete. So do the warm-up problems, submit them. I'll give you feedback if they need some help, and then move on to the level up ones, and I'll give you feedback on those as well. So let's work through this practice here. So click on Practice, Area of Rectangle. And on this particular page, we're not actually writing a program. We're not writing a program and compiling it. We are just constructing a program by dragging these parts of the program into the right spots. So over here on the left, this is kind of like a puzzle. We've got all the puzzle pieces. And over on the right-hand side, we're going to construct a working program. And so what this program is going to do is it is going to prompt the user for the height and width of a rectangle in that order, calculate the area, and then display the result. And then if we think we're correct, we'll click on Get Feedback, and it will tell us whether we got it correct or not. So let's go ahead and do this. What do I need to do to start this off? Which of these puzzle pieces should I grab from the left-hand side and put on the right?
The preprocessor directive.
Good. Let's take this include, and we'll move it over here. Good. Hannah, good. What's next?
Int main.
Int main. And then next. Yep, open parentheses. And then
Would you do the integer height with an area?
yeah, let me go ahead and declare these. Now I'm going to have to indent this, right? So I'm going to go ahead and just actually indent it. Next.
Printf, enter width.
Now, is that the first thing we enter?
Oh,
No,
enter
only
height.
this we do height first. What's next?
Enter the
Scanf height.
Mm-hmm. And then?
Printf, enter the width.
Good. And then the scanf for that.
area equals width times height.
Mm-hmm. Do the calculation. And there's only two things left. So that will be the printf to display the results, and then finally close it all out. And then we'll click on get feedback, and it all lights up green, so we know that this is good. So warm up 1.0 is essentially just type in that program and get it running. Let's go ahead and try it. So I'm going to create a new file. Let's call this area.c. And we start off with the preprocessor directive. Now I like to put a blank line in between my different sections of the program. So the preprocessor directives go at the top, then a blank line, then any global variables or constants, then a blank line, and then functions, and blank lines separating each of the functions as well. So kind of like paragraphs you write in an essay. Unfortunately, with that drag and drop thing that I just did, I can't put in a blank line. So that was not there. But when you actually write your program, please put one in. The compiler doesn't care, but there was a famous programmer, I think it was Donald Knuth, who said that programs are to be read by humans and incidentally executed by computers. It was a very powerful statement that he said there. He said that you should write programs so that other humans can read them. That's your primary concern. Your secondary concern is whether or not the compiler can actually execute your program. So make them readable to humans. Don't worry so much about whether the compiler can read it. So we started off with int height width area. And again, I like to leave a blank line in between my variable declarations and the rest of the program. Printf, please enter the height of a rectangle. And then scanf %d inside quotes, and then ampersand height. Then printf, enter width, scanf %d, ampersand width, area equals height times width, and then finally a printf, the area is %d, new line character. Go ahead and save this. I'm just going to use Command S, but you'll see this dot change to an X. And let's compile it. Clang area.c. No news is good news, so we'll try running it. Enter the height of a rectangle. Let's go with 5. Enter the width. We'll go with 10. So it should display 50 if this works, and it does. Now, this program, of course, doesn't know what is sensical and nonsensical values, so I can do like -7 for the height, and I can do 12 for the width, and it says the area is -4, but there's nothing in our program that does any kind of error checking, and I'm not worried about that at this point. The goal of this is just to basically get input from the user, do a calculation, and display the result. Any questions on that one? Okay, let's look at our other two warm-up problems. The next one is called add fractions. So in this one, we're going to write a program called sumfrac.c. Prompts the user to enter two fractions of the form numerator / denominator. And then the program is going to add those fractions together and display the resulting sum. You don't have to reduce the fraction if you don't want to. Before I move on to that, let's change this area program. I want this to... Actually, let me just write a new program here. I like to do this where you have your programs that you need to write, and what I'll do is I'll write a very similar program that's not identical, but will contain the same concepts you need to be successful in writing your warm-up or your level-up programs. So I'm going to call this program larger, and what it does is it prompts the user to enter two numbers, and then it tells you which one is the larger one. So we'll start off with the include standard.io.h, as we always do, int main, and now I'm going to have them type in two numbers. Let's go int a comma b, those will be my two integers, and printf enter two integers. Now, instead of having them enter the numbers separately, I'm just going to have them enter it on the same line. So I'm going to use %d, and then &a and &b. So the user is just going to type in the two numbers with a space in between them. I'm going to use an if now to determine which one is bigger. So if a is greater than b, I will print out the larger is %d, else printf the larger is %d, b. So if a is greater than b, I'll say the larger one is a, and if b is the bigger one, then I'll say the larger one is b. That's my whole program. Okay, let's compile that. So enter two integers. Let's go 3 and 5. Since the larger is 5. And let's switch it around. Let's make sure it works in the other direction as well. So I do 9 and 2. Then it says that 9 is the larger one. So that's all fine and dandy. But it kind of requires the user knowing that they have to enter a space in between the two numbers. What if we want them to type in a comma? So I want them to type in the first number, comma, and then the second number. What do I have to change in my program so that it will allow a comma in between the two numbers?
Can we just add a comma in the string format?
Yes, exactly. I'm going to put a comma in between those two %ds. I'm going to go ahead and save it, compile it, and we'll run it. And now I go 3, 5, and it still works. So by putting the comma into the format string, we tell scanf there must be a comma in between those two numbers. And in fact, if I don't put the comma in, it's not going to match the format and it's not going to work. Let's try it out. Let's put in 9 space 2. So I'm not going to put the comma in there. And it says the larger one is 32765. Well, that's crazy. Where'd that come from? I didn't type in that number. Who put that there? Can you tell me?
Is that the comma?
No.
Is that what was previously in the memory space?
Yes. So what's happened here was we typed in scanf %d, comma %d, and then we have these two variables a and b that we put the input into. And what I typed in was 9 space 2. So what scanf did is it starts scanning through my input from left to right, and it checks to see if my input matches this format. So the first thing on the format is a %d. It says, okay, I'm expecting an integer. Is 9 an integer? You bet, it is. So it's going to put 9 into A. And then we come across a space. Now a space is not part of an integer, so it knows the 9 is done. But the format says the next character after the integer needs to be a comma. We typed in a space. So at that point, scanf says, abort, abort, we're done, can't handle this, and it stops. So what happened? What's the result of doing the scanf? Well, there's 9 in A, and what's in B is what just happened to be in there before we did the scanf. So it's just a junky garbage value. So when it does the comparison, it says, oh, B is bigger because 32765 is bigger than 9, and it prints out that one. In fact, we could see what's inside those values before we even do the comparison. If we just do a printf, A is equal to %d, B is equal to %d, A comma B. We'll just print out the values of A and B. We'll run this again. Oh, I need to compile it first. Enter two integers, 9 and 2. We can see that A is 9, and there's a dot here. I didn't mean to put a dot. And B is 32, oh, this time it's 32766, so it's actually different than it was before. So it says the larger one is 32766. And compile it again and run it again. Let's put in hello, goodbye. Those are my two inputs. And it says A is 0 and B is 32764. So the value of B seems to be more or less random, right? It's still kind of in the same ballpark, but it's changing every time I run the program because it didn't initialize either of the variables. So A happened to get the value 0 and B happened to get some random value. So that's what's actually going on here. Scanf is aborting as it does the scanning because it doesn't match the format and it leaves any variables it hasn't assigned to untouched. That's a big difference from Java. Java at least would have said both are 0. There's a question here. Is there a way to check the format in scanf? Well, not really. Scanf is kind of stupid. I mean, all it does is it just blindly follows the format, and if it doesn't follow the format, it just aborts. What you can do, and this is beyond the scope of what we're requiring for the assignments right now, is you can check the return value from scanf. It actually returns a number back to your program. We're not doing anything with a number, but it does return a number, and it will tell you how many variables were successfully assigned. So if I typed in 9 space 2, it'll say 1, because the 9 got assigned, but the 2 did not. So that's one way you could tell whether the format completed or not. If you know how many variables are supposed to get assigned and you get less than that, then you know something went wrong. Now, let's try something else. Let's go ahead and run the program again. But instead of typing in 9, 2, I'm going to type in 9, space 2. And that one seemed to work okay. In fact, 9 goes into A and 2 goes into B. Let's try switching it around. Let's do 3, 5 with a space after the comma. And that one also seems to work. So even though the space is not in my format, it still worked. Well, let's try shaking things up a little bit more. Let's do 3 space, space 5. So now I'm putting a space in front of the comma. And now we get 3 in A, and B is a junky value. Whoa, that's crazy. So like I said, Scanf is kind of stupid. It's really just checking to see if something obeys the format. And it's following a very strict set of rules about what that format needs to look like. So here's kind of what it looks like. So if your format code is %D, then it follows this diagram here called a state diagram in order to pull the characters in from the user's input. It enters the state diagram over here on the left. And then what it does is if the character is a white space character, like a space or a tab or an enter key, it just throws that away and loops back and gets the next character. If it's anything else, like if it's a letter or a symbol, something that's not an integer, then it stops. It just aborts at that point. And then finally, if the letter that it read in was a 0 through a 9, so if it was a digit, or if it was a minus sign for a negative, then it moves to this other state. And that's where it starts consuming the rest of the number. So for an integer, it also has to be more digits, and anything else says, okay, I'm done. I'm going to assign what I've got to the variable. Okay, so if the user types in something like 93, then this 9 is a digit, so it pulls that in and then goes to this other state. And then we read in a 3, so that's over here. It pulls in that number, and then we're done at that point, and so we go and assign this number to the variable. Okay, but if we, whoops, I want to erase that. But if we were to type in something like 23 skidoo, so it enters over here. We've got a 2. That is part of an integer. That's good. We've got a 3. That's also part of an integer. And then we encounter an S. Well, the S says, I'm done. The 23 goes into the variable, and the rest is, we just abort at that point. And the skidoo is still sitting out there, waiting to be read in by the next format character, or format string. So what you can do in order to accommodate the user potentially typing in some extra spaces is you can put a space in the format string. I'm going to put it in front of the comma. And the reason for that is, if you look here in the state machine, we'll see that if the format string is like a %D and there's white space, then those are just simply thrown away. What that means is that in my program, if I run the program and it asks for a single number, like someone's age, the user can type in like space 35 and press enter. And those initial spaces will get thrown away. Scanf will just skip over them. Okay, so any white space that comes in front of the user's input is just simply ignored. backing up a bit. That's why in my first versions of the program, way up here, I had to separate the numbers by a space because that space gets ignored. Okay, that's my separator between the two numbers. As soon as it encounters the space, it knows the first number is done, and then all those intervening spaces are just simply thrown away, and the second number goes into the variable. Here, I've put a space in front of the comma, so as soon as it encounters a space, it knows that that first number is done. Then we've got a comma, and then if there are any more spaces after the comma, it will throw those away as well, because the format specifier for a number says initial spaces are thrown away. So let me compile that. We'll run it. Now I can do 9 space, 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 comma, space, 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 2. And 9 goes into A, 2 goes into B, and it successfully computes the larger of the two. And I can also eliminate the spaces entirely, and it still works. So Scanf is a little bit flexible, but you have to go out of your way to make it flexible like this, like that. Otherwise, it's just following a very simple state diagram in order to pull those characters in and put them into the variables. Any other questions for this? Okay, it's 11 o'clock now. We've been going at this for an hour and a half. This will be when we take a little bit of a break, and it'll give you a chance to go up and get some coffee, get something to drink, go to the bathroom. We'll come back at about 11:10, and then we'll pick up where we left off. We'll go over the other assignment for you. Actually, we'll finish talking about the fractions assignment, and then we'll go over the other couple of assignments that you need to do this week, and then that should take us to about 12 o'clock. Okay, so let's go ahead and take a break. What I'm going to do is I'm going to pause the Zoom recording so that those of you who are watching on Zoom later on don't see the entire break, and then there'll just be a little gap in the recording. Okay.
Recording stopped.
Okay, I have no way, however, of pausing the YouTube recording, so it's just going to continue, but I'll play some music while we're waiting. How are we all doing?
Good.
Are we getting something out of this?
For sure.
So I like during these live sessions to not only just go over the stuff that was in the book and the stuff that's on the assignment, but all these things about like how Scanf and Printf are actually working under the hood. Not only is that to me really interesting, but I hope that for you it gives you a little bit of insight actually what's going on, and maybe it explains why your program is behaving in a strange way.
Yeah, that's very helpful to me to know those things.
Yeah. I mean, really, things like Scanf and Printf were designed and written way back, like in the 70s, when computers were slower, had less memory, and so they weren't really designed to be robust, like error checking and let you know what's going wrong. They're very simple, and I guess the term there is brittle, right? If the input you're giving it is correct, it works well. But as soon as the input is not quite correct, it just crumbles and falls apart. Someone was asking, is there a way to compile and run the program all at once? And someone posted there that you can do something like this. You can go clang area.c and then 2 ampersands /a.out. And so it will compile it and run it in one step. If it compiles successfully, it'll go ahead and run it. If it got an error, it won't run it. So if I introduce an error, like I miss a semicolon, and then I run this again. Oh, did it compile? I did not expect that to happen. I actually expected it to not work. Oh, did I save it? I did save it. Oh, it's because I'm doing area.c. I need to be doing larger. Clang larger.c. Here we go. And /a.out. Here we go. So we got an error, and it does not run the program. However, if I fix the error and I save that and I run it, then it compiles it and runs it in one step. You still have to type in the command, however. It just saves you, I guess, one little command at the expense of having to write out the longer command to begin with. Later on in the semester, we'll find out how we can automate all this. So you just type in one single word, make, and then it just builds it for you, especially if you have a multi-file program that can save you a lot of steps. Oh, I don't have to delete the a.out program if it just overwrites it. So if it compiles it, it'll just overwrite that executable. If it does not compile successfully, then the a.out will still be there. It'll just be the old version, the last successfully compiled one. No, it doesn't produce an a.out. So if I got an error compiling it, then my a.out will still be the previous one, the last successful compile. So let me try that. If I the larger value is A. The larger value is B. Okay, but let's say I made a mistake. So if I run this program, or run this compile, it got an error, so it did not actually successfully compile it. But if I now run the program, it actually works, right? And what I've got here is I've got the old version, the old previously successfully compiled version. So now my source code and my executables are out of sync from each other. So if I correct the program and then compile it again, it now overwrites the executable with the new version. So the two ands here on the command line tell the shell, run the first command, and if that was successful, go ahead and run the second command. So do this and this, and the and here means do the first thing and the second thing if the first thing was successful. If the first thing was not successful, then the second one will not run. Yeah, if you want to do both of them, then you use the OR symbol. So you can put clang larger.c or /a.out, and then it will run both. It will do the first one, and then it will do the second one, regardless of whether the first one worked or not. So we'll come out of our break in a few minutes. Then I'll show you the other programs you need to write this week. And then we'll field some more questions, and then that'll be it. Looks like I'm losing some people. They're down to 3 people on Zoom.
They probably will come back. Or not.
Oh, one's back.
Yeah.
Oh,
I'm here. I'm just doing homework for CS26.
I just realized I didn't have my video on this whole time. Here I am. I have so many things going on my screen. I have to have a checklist now. I need to write a checklist. It says, remember to reset the mixer first, right? I have to add that now. And then remember to turn on your video. So people on YouTube have been able to see me, but you on Zoom have not been able to see me. You just saw my little icon that's just waving at you. And I hate it when I do that because sometimes I'm like showing things on the screen and I expect that you can see me even if you're looking at my laptop screen. I expect that you got a little corner or something in your corner and we can see me, but I forgot to turn on my video. The unfortunate thing about Zoom is it's like not a standard application. It has its own toolbar, and it's got a few, at least on the Mac, it's got a few menus, and those are standard menus. And the nice thing about using standard menus, the kind you see in any application, is I can automate those things. I have a program called Keyboard Maestro that allows me to essentially send virtual keystrokes to an application. I can use that for things like starting and stopping the Zoom recordings. I have a control panel, a Stream Deck, right here. And I've got a button here for starting and stopping the Zoom recordings. And all that does is it sends the keystrokes to the menus to start and stop the recordings. That's kind of nice. But anything that appears in that toolbar, the Zoom toolbar, is not a standard user interface element, and so I can't send keystrokes to that. And so there's no way for me to just send a keystroke to say, start and stop my video, because as far as I know, those are not present in the menus at all. I also can't send keystrokes to change the quality of the data rate that's coming out. Like when I show a video clip, I want to increase the data rate coming out so the videos don't stutter. Well, those are in the non-standard toolbar for Zoom. It's not in the standard menus. And so I can't have a button to say increase the video rate and increase the quality. I have to go remember to do it. And so I've been begging the Zoom people, please, anything that's in the toolbar, please also put it in the menus so that I can automate those things with my Stream Deck. I don't know if they're listening to me. But that's what I want to be able to do, is basically have a button for everything. And so I should have a button that just says, check to make sure everything's set up correctly. Check to make sure that the YouTube is streaming, that the Zoom is recording, that my video is on. And just one button just to double check everything. And I can't do that because the Zoom people decided to make their own custom toolbar. And even if there weren't keyboard shortcuts assigned to those things, I could still have Keyboard Maestro virtually pull down menus and select menu items. So I could say pull down menu number 4 and then select menu item number 6, right? And there would be a little flash on the screen, but at least it would do that. But again, the Zoom toolbar is not a standard user interface component, and I can't do that. So it's kind of frustrating. Do I plan to upload videos on different topics on YouTube as before? Well, I have my 2 classes that I'm doing. I have the C programming class on Tuesdays and Thursdays. Then on Mondays and Wednesdays, I have my discrete structures class. And that one does include a variety of topics. So if that's what you're looking for, go ahead and watch those. and you'll find I have a playlist on my YouTube channel that includes all the videos from that course, and I have a playlist for this course, and then all the other stuff that I used to do, like DNS and Java programming. I don't do that much anymore because my focus now is on doing these courses online.
Mr. Brown,
Yeah.
what does the structures entail, really? What's it about?
Well, in a nutshell, it's a foundational introduction to theoretical computer science. So it's all the theoretical stuff that forms the foundation for a lot of the stuff you see in programming. So we talk about things like representing data in binary, decimal, hexadecimal. That's what we're doing right now. Later on, we'll be doing Boolean algebra, logic, gates, and circuits. So basically the building blocks of a computer. Then we're going to get into modular arithmetic, cryptography, sets, probability, combinations, permutations, graph theory, programming language parsers and grammars and compilers. So it's a lot of a little bit of a lot of stuff. We go over the math foundations behind it, and then we also do some practical programming assignments where we kind of apply those mathematical principles and show how they relate to your programming, your computer science courses, your other computer science courses.
Gotcha. Okay, thank you.
You heard that discrete structures is one of the hardest computer science classes?
Well, don't tell me that. I'm in it.
Yeah, I've heard a lot of people have struggled with that class because it's kind of like math almost, I guess.
Yeah. But I'm not some hard-nosed professor that makes life hell for you.
Do you offer that class in the summer? Do you know if Sierra College does? Is it
don't.
recommended?
I personally don't.
Okay.
I don't remember if it's offered in the summer.
What about the fall?
Definitely. It's offered every semester. Every fall and spring.
Are you teaching it?
Yep.
Alright.
Can I ask a quick question?
Of course.
When I'm using Canvas on my web browser and I go to the calendar, only one of my classes like actually shows up with assignments. Is that just me, or is that something on your guys' end that you have to activate?
Look on the very right-hand side, and there'll be a list of all your courses. And chances are you've only got one of your courses checked.
Okay. Let's see. Ah, that's what it is. Okay, because I was like,
Yeah.
I have it on my phone,
Mhm.
but I don't have it on the web
Yeah.
browser.
So you found it, check the other boxes, and then the other
Yeah.
showing up.
Cool. All right. Because that's mainly what I use to keep progress of all my stuff.
Well, let's come out of the break and we'll go over the rest of the assignments, answer any other questions you've got.
By the way,
Yeah.
can we call you Doc Brown?
Doc Brown,
Doc Brown?
like from Back to the Future.
Yeah.
Just mess up my hair some more and put a little talcum powder in it.
Uh,
Recording in progress.
All right, so we're done with our break, and here we are back. So let's go back to our add fractions assignment. So I want you to write the program so that the user enters in two fractions, and then it adds those fractions together. Now the key thing here, two key things. One is C doesn't know anything about fractions. It knows about integers and it knows about doubles and floats, but those are not fractions. So you need to keep track of the numerator and the denominator yourself in separate variables. When you're adding them together, you need to use a formula like this. If you're adding the fractions a over b plus c over d, you can calculate the resulting sum with this formula shown on the screen. So you're going to need probably 6 variables: a numerator and denominator for the first fraction, a numerator and denominator for the second fraction, and the numerator and denominator for the sum. The second thing is I want the user to be able to input the fraction as the first number, a slash, and then the second number. So use that technique that I just showed you about entering 2 numbers with a character in between in order to get that fraction read in correctly. This is a warm-up problem because one of the purposes is to get you used to using Scanf's string pattern matching facility. Don't worry about reducing the fraction. You don't have to do that for this assignment. Just simply add the 2 fractions together, and if you end up with a weird numerator and denominator, that's okay. So you're going to turn this in the way you've turned in the other programs. You're going to download the program to your computer. You can do that easily from there. You just go File, Download, and then it will download the C program to you. Or you can right-click on the file and do Download as well. And then just upload that C file to this page, and then I'll take a look at it. So an optional extension that you could do to this program, it's not required at all, and it won't change whether or not you get a complete or incomplete on the program, is you can go ahead and try to express the fraction as a mixed fraction. So if you get a numerator that's bigger than a denominator, then go ahead and give it as an integer and then followed by a fraction. So if I added 3/5 and 7/9 together, I would get 1 and 17/45. Okay, so just something to do if you found this program fairly quick and you want a bit of a challenge. Next program is called flag. You're going to prompt the user to type in the height of a flagpole, and any value from 3 to 14 is valid. And then you're going to display a flag with the flag pointing to the right. The flag itself is of a fixed size. The flag is always 3 rows tall and 5 rows across, or 5 columns across. Sorry, 8, not 5. 8 columns across, 3 rows tall. And then whatever is left over is going to be for the flagpole. So if the user types in 8, you'll have 3 of those for the flag and then 5 for the actual flagpole. This will probably involve some loops. So again, a little exercise in just getting user input from the user and then using some loops to calculate the size of this picture. Optional extension would be if the user types in the height as a negative number, you're going to display the flag upside down. And then the final program to write this week is called grilling. This summer, I did a lot of cooking on the barbecue grill. They come in different sizes, barbecue grills do. Let's write a program to draw a picture of a grill. So the user is going to supply the width and height of the grill in that order, and then you're going to draw a picture of that grill. So it's just going to be like a whole bunch of lines going across the page with some nice border around the frame of the grill. So here's one that is 12 wide and 4 tall. Right, looks like this. So to draw this picture, use plus signs in the corners, vertical bars on the sides, and then dashes everywhere else. Do a little bit of error checking. Make sure that the width is at least 2 and no more than 30, and the height should be at least 2 and no more than 12. Anything else should display an error message indicating what went wrong, a gentle reminder of the valid values, and then just exit the program immediately. So in my examples, I often show you an example of how the program should run. I show the user's input in bold, and that's just there to make it stand out in the example so that you can tell the difference between user input and what the program is displaying. You are not expected to display anything in bold at all. And then turn in your program as you did the others, download it to your computer and upload it to Canvas, and then I will take a look at it. So all I'm checking for is to make sure that it works correctly. I'm checking your style as well. Are you indenting nicely? Are you using variable names that make sense? Are you following the format of the C program that I talked about? The includes at the top, any global variables, and then your functions down below. You shouldn't need any global variables for these programs. All your variables should be inside of main. These programs are nominally due in a week. They're not really actually due, but if you're keeping up with the pace of the course, try to have them done by next Thursday. That'll give us also an opportunity to talk about these programs. We'll do it on Tuesday as well. If you have any questions about these programs, something you just can't overcome, then you can come on to Zoom and we can answer your questions. There's also help available for computer science students. If you look in Canvas, there will be shortly a link to our, actually there'll be two links. First is on our main page, there is a link to the Computer Science Discord server. So you can click through to that, and then you can join the channel that's appropriate to the classes that you're taking. Also, we have lab assistants, student assistants who can provide some light-duty tutoring and help you out with technical problems, and there will be a link to their Google Calendar posted on Canvas in the module section as well. And so they're available most afternoons and evenings. I think I have 3 helpers. There's Ahmed, Terry, and Zed, and they can help you out with any of these assignments as well. They're available to chat via Zoom. They can also chat via Discord, and you can do things like screen sharing so that they can look on your screens and they can help you out debugging your programs and getting over some of the problems. And of course, also there's my student hours on, what do we got? Mondays and Tuesdays from 11 to 12 o'clock. There's a separate Zoom link posted on Canvas for those as well. So after my Monday and Tuesday classes, I go into student hours and I'm available for an hour between 11 and 12 to answer your questions as well. So a lot of ways to get help. And finally, if you need some one-on-one help with somebody, if you're just really stuck and you need a tutor for this class, you can contact the Tutor Center and they will put you in touch with a student who can give you an hour per week of one-on-one tutoring. So it's just you, you're not sharing your time with anyone else, and that's totally free. So we've got our student assistants. There's 3 of them available most afternoons and evenings. We've got the Discord chat that you can get on to ask your classmates questions. Also the tutors and the lab assistants hang out there as well. And then finally there's the Tutor Center that's available. So lots of resources for getting help on not only this class, but your other computer science classes, my discrete structures class, and any of the others that you might be taking at our college. Let me think. Was there anything else I needed to cover? Oh, let's do this here. So you might have noticed when I was typing in commands down here on the shell, that in some cases it looked like I was able to type the commands very quickly. Every time you type in a command, it remembers what you typed in. And so it maintains a history of all the commands you have typed in, actually going back all the way to when you first logged onto Thea for the first time. You can get access to that history of commands by just hitting the up arrow key on your keyboard. So I just press up once, it brings back the previous command that I typed in. If I press up again, it brings back the one previous to that. And I can keep hitting up and it goes back through my history of commands. And you can just look for the one that you need. As soon as you see it, press enter and it executes that command. Another useful thing that could be used for is if you typed in a command but you made a typo on it. You didn't type in one of the file names correctly, or you didn't type in the name of the compiler correctly. You hit up arrow, it brings back that command, and then you can use left and right to scroll left and right through that command, fix your problem by just hitting delete or typing the characters you need to fix, and then just press enter. And a little hint there, you don't have to go to the end of the line to hit enter. You can hit enter at any point. So for example, if I want to recompile this larger.c, but let's say I misspelled the name of larger and I forgot to put that A there, I could just press A and then just press enter and it will compile the program. So here's kind of a summary of what I just said. You can use up and down to scroll through your command history. You can use left and right, delete and enter to make corrections to the command line. Control A is a very quick way to go to the beginning of the command line. So if you typed in a long command and you want to go to the beginning of it, you press Control A and it zips your cursor over to the beginning. If you want to go back to the end, you can use Control E, E for end. And then if you just want to abort the command, or you discover that your program is running, but it seems to just hang there and do nothing, then you can always press Control C, and that will cancel or abort your current command or your current program, and it will get you back to the prompt. For example, if I'm typing in this long compile command, and I decide I don't actually want to do that, I could laboriously hit delete until I delete the whole thing, or I could just simply hit Control C, and it will cancel or abort that command and it won't run it. And the other thing I was talking about is if you're running your program and it just seems to just sit there and do nothing, like you expected the program to end, but it didn't, it just sat there, you can also just press Control C on your keyboard and that'll cancel your program, abort your program, and get you back to the prompt. Why Control C and Control A and Control E? I thought on Windows those meant things like copy and select all and things like that. Well, these keyboard shortcuts predate all of that stuff. Windows came about in the 1990s, and the Linux command line has been around since the 1970s. So these control characters like Control C and Control A are left over from those early days of Linux and Unix environments. And back then, Windows did not exist. And so things like copy and paste and select all were not even things that the Linux people were even thinking about at that time. And so when you're using like the Thay environment, Control C means abort. It does not mean copy. In order to actually copy something, you have to highlight it and then right click and go, here we go, and go copy. If you're on a Mac, it's kind of nice because you can just go Command C and you can copy that way. But on Windows, you have to right click and do the Control C. Do the menu item. There's no keyboard shortcut for it. Any questions about that stuff? Okay, so you've got your programs to write for this weekend. You've got the basics of using the command line shell, how to compile your programs, how to run them, how to turn them in. So I think we're set. So we got about 15 minutes left. I want to go dive a little deeper into some other stuff that will hopefully also give you a little bit of insight as to why things are the way they are on programs that you write in a command line environment. And so one of the things that comes up is, what's the difference between printing something out and returning a value from a function? Well, we haven't really gotten into functions here, but if you take a look, first of all, there's one thing here. Is notice that main is declared to return an int, but nowhere in here is there actually a return. And the compiler isn't complaining about that either. Normally, if you declare a function to return an integer and you don't actually return an integer, the compiler will flag that as an error and tell you, you declared this function to return an integer, but you didn't return anything. That's an error. But for main, that's different. For main, if you do not include a return statement, it will implicitly put a return 0 at the bottom for you. This is special just for main. If you don't put in a return, the compiler will insert a return 0 at the bottom for you. Well, where does that 0 go? If you've taken the Linux or Unix class, you've seen that number come back to you as what's called the status code or the return code from a program. When you run a program, it returns that number back up to the shell. The shell is this thing right here. So that return 0 comes up back from your program and gets put into the memory of the shell. And then your shell can look at that variable and can glean some information out of it. So for a typical Linux or Unix program, a 0 means the program worked okay. Nothing went wrong. Anything else means that something went wrong in your program, and it's up to you, the programmer, to define what those numbers mean. You know, typically 1 means like maybe the user didn't invoke the program correctly. Maybe a 2 might mean a file that it was looking for wasn't present. So you get to define what those numbers mean. So in your program, you could say return 1. Your program will still complete successfully, but that 1 will get returned up to the shell, and the shell can look at that number and display maybe an appropriate error message to the user. So that's what that's for. So if you return a number from main, it goes back up to the command line shell. If you don't return anything, the compiler will insert a return statement for you. But a question that comes up is, what's the difference between returning a number and printing out a number? Like, you know, when I print something out, can I get access to that? If I print out the number 5 on the screen, can later on my program go and retrieve that number 5 and use it for something else? What do you think? I'm asking you, people on Zoom. Can your program get access to it?
Probably not.
No, it can't. Even though it's sitting there on the screen, like it must be held in the computer's memory somewhere, your program can't get access to that. And the short answer is because what appears on your screen is separate from your program's memory. And the reason for that is, again, historical. See, back in the 70s and 80s, we didn't have, we meaning, you know, the general population, didn't have personal computers like we do now. Yeah, you know, computers were fairly rare. They were big, they were bulky. Like I said, back in the 70s, 80s, they were like the size of a washing machine. So a typical multi-user, state-of-the-art computer would have been like roughly the size of a dishwasher or a washing machine. And, you know, they would have looked something like this here. This is a VAX 11750 by Digital Equipment Corporation. And it's about the size, again, of a dishwasher. And if you were to open up the front panel, you would see all these cards inside of it. And, you know, one of these cards has the CPU, another card has the memory, another card maybe runs the disk drive, another card in here might do the input and output to the screen and keyboard. You know, another card in here had another purpose. Another card maybe devoted to doing math operations. So you could basically change how the computer worked and the features you could have on the computer by inserting and deleting these cards in the computer. But then if you wanted to interact with the computer, and I can speak from personal experience, this is the way it used to work when I was in college, more or less, this is the way it used to work, is the computer was in one room where it was nicely cooled and ventilated, and there were people to watch over it and make sure it was working correctly, because these things broke down fairly frequently. But then the actual keyboard and output device was in a separate room. We had actually a whole room, kind of like a computer lab these days, where you got all these computers set up on tables, but what was sitting there in these computer labs was just a screen and a keyboard. There was no actual like computer there. The computer, like I said, was in another room, and multiple people could use this computer at the same time. If there were two people sitting next to each other, or maybe they were sitting, in the same room, they were both accessing the same computer, but they had a separate screen and keyboard. And so when I was going to college, this was the way we interacted with the programs, the computers that we were writing our programs on. And that we not only had a room full of these things called terminals, but there could be other rooms around campus. And so we had about 5 or 6 of these rooms. There were ones in different buildings that were all accessing the same computer. But how did the signals get from that central computer to these terminals? Well, there were cables physically running from the computer all the way to these other buildings, and then into the rooms where these terminals were. And that's what this other thing is. These are just pictures I found on the internet. This is called a terminal server. And what this device is you've got basically one connection that comes in from your central computer, and it goes in here, and then these plugs all run out to these terminals, which look like just a screen and a keyboard. And so here's what one of these cables might have looked like. It's got this giant 25-pin connector on it, and you can see on the back of that terminal server you've got about 20 of those plugs. So each one of those terminal servers could serve 20 of these terminals, and that's how multiple users could use that one central computer at the same time. And so this would plug into the back of the terminal server, and then these cables would go down into the floor and into the walls and then into that other room where the actual terminals were. Okay, so you have basically a cable that comes and plugs into that one, and then these all ran out to terminals, which were just basically a screen and a keyboard. So that was state-of-the-art computing back in the 80s. But prior to that, the terminals didn't have screens and keyboards. They used something called a teletype. And that's what this is here on the right-hand side. A teletype is a printer and a keyboard. And it's not a printer like a inkjet printer or a laser printer like we have today. These were old dot matrix printers, the old style printers that made all that clattering noise as the printhead went back and forth. Or it could have been almost like a typewriter with its little arms that go up and down and physically striking the paper and putting the ink onto the paper. Let me see if I can show you a video of a teletype in action. Let me do a little YouTube search and see if I can pull something up.
This is the world's first.
Oh, we don't need to see this little ad here of somebody pulling earwax out of their ear. Thank you. Don't need to see that. Ah, here we go. Let me just scroll to an interesting part of the video. Here. Oh, I also need to increase the bandwidth coming out of here. Okay.
And not any paper tape, but the newfangled 1-inch wide tape, like the yellow one here, that can fit 8 bits. That's a whole 3 more than the old
Here we go.
5 machines in one. Just imagine what you could do if you had one, like this lucky fellow in 1967. You could check the weather in the morning, receive quote alerts, and even personal messages right next to you from your bed. Clearly, this is the machine that is going to bring us a better future. In this demo, I will connect it not to a computer, but to a 1974 HP Terminal, one of the machines that would eventually dethrone the teletype, but is still compatible with its old 20 mA current loop and can connect with it at the blazing maximum speed of 110 bauds. So I think we're done, ready for demo. Line. So here I am sending an ASCII message pre-recorded on the HP Terminal magnetic cartridge to the teletype. I have the teletype set up to print the message and also punch it on the tape.
So you can see the blazing speed at which this thing printed at, right? But the whole point there is that once that character appears on that teletype and it gets printed on the page, it is now committed to that page, and there's no way for the computer to get access to what's been physically imprinted on the page itself. So instead of going to a screen and a keyboard, these connected up to these old teletype devices. And to this day, when you use a command line environment, the machine that you're using, the Linux or Unix machine you're using, still kind of believes that you are talking, or it is talking, to a teletype. When it prints something out to the screen, it thinks that it's going to a teletype that's going to physically imprint that on a piece of paper. So when it sends out, let's say, the letter H, right? That letter goes down into the terminal server, and then it comes out one of these cables, and it goes to the teletype. And so the letter H doesn't really physically go down the wire. It turns it into the ASCII code for an H, and then it sends the bits for the letter H down the wire, and it goes to the teletype. The teletype then just physically prints it on the page, and at that point, the H you can see on the page, but to the computer, it's gone. There's no way to get it back again. Then maybe the next character it prints out is an E. So the same thing happens. It turns that into the ones and zeros for the letter E. It sends that to the terminal server. The terminal server then sends that off to the teletype, and then the E gets smacked onto the page. If you then press a key on the teletype, the reverse happens. Let's say you type in, I don't know, an L over here. So your teletype turns that into the ones and zeros that represent the letter L. And then it goes, it goes back into the terminal server and then back into the computer. And as far as your teletype is concerned, that L is now gone. There's no way for your teletype to get it back. So when you do a print in your program, those characters go to your screen. Let me switch back over to here. Those characters go onto your screen, and then there's no way for your program to get access to those, because as far as it's concerned, it has sent those bits down across the internet to appear on your screen, and now it's committed. Those are gone from your program. So when you do a print, it's not the same as doing like a return or setting a variable in your program. I see this somewhat frequently out of students who have just taken one semester of programming. They don't know the difference between doing a print and a return and assigning a variable, because to them it all results on something appearing on the screen, and so that must be something your program can get access to. But the reality is, at least from a command line point of view, anything that's sent to the screen is now gone, and it can't get access to those things. What this also means is that all that the computer knows is what it has sent to you. For example, if someone was to take that teletype and turn it off, well, the computer just keeps sending the data out. It keeps going down the wire. It just goes to nothing. The computer thinks that it sent the word hello out to the teletype, but nothing appeared on the screen. Nothing appeared on the paper because someone turned it off. The computer has no idea that happened. The reverse could also happen. I could type the letter L on the teletype, And if someone had clipped the wire between the teletype and the computer, I would think the L went to the computer, but the computer never received it. So I hope that gives you a little bit of insight as to what's happening when you actually print something out. When you say printf and then some string, it's sending the individual characters to your computer, and once they disappear down that wire going to your computer, they're gone. The computer, the program that you're writing can't get access to those things. It also can mean that something else, maybe you have two programs running simultaneously. They're both outputting to the screen. So all those characters get jumbled up together. They appear interleaved on your screen, but program A and program B have no idea that that's happening. And they think that they are writing to your screen simultaneously, not simultaneously, but independently and separately. They have no idea that both programs are running. So do you have any questions about that? No? Nothing about that? Okay, well, that's pretty much all I had for you today. We got a little introduction to writing programs in C using our programming environment. We learned a little bit about how the Printf and Scanf work as far as that state machine that's reading in characters and scanning through your input. And then finally a little bit about the history of old 80s style computing dating back to when Linux and Unix machines were designed, and what was kind of the model of computation back then, and why is it that when I print something out to the screen, I can't get access to it later on. Someone was asking, can I still get an ad code for this course? Yes, just shoot me an email and I will send you one. When will be the next session? So for this particular course, the next one will be on Tuesday. So 5 days from now at 9:30 in the morning Pacific time. I have my other course Mondays and Wednesdays at 9:30 Pacific time. If you go on my YouTube channel, I've got a playlist for C programming, and there you can see the sessions that I recorded last year for the last term's classes. And that one picks up about halfway through the semester. So what you're seeing now is stuff that I never got around to recording for YouTube. And I'm just posting it on there for anyone who wants to watch it and learn something from it. Okay, so my Zoom students, there's a last chance to ask some questions before we sign off for today.
No, I'm all good. Thank you. Have a nice day.
Okay, you too.
Yeah, thank you.
You're welcome. So take care. YouTube people, I'll sign up with you in just a moment, but the Zoom people will go first. And I hope you all have a great day and enjoy this weather while it lasts. I think next week we're expecting some rain.
All right. Thanks.
All right.
Bye.
Take care.
Thanks.
Bye-bye.
Bye.
Record.
Okay, now, YouTube folks, I have to sign off from you separately. So I do the Zoom one first, and then they usually do the YouTube one next. Do you guys have any questions? Unfortunately, YouTube is on a bit of a delay. So I ask a question, and then I don't hear from you for about 10 or 15 seconds. No? Nothing? We'll get plenty of opportunities as this course goes on to talk more about the history of computing and look at some old computers. I have some old stuff back here. I've got some old stuff in my closet over here, so I'll bring those out on some of these other days, and we'll take a look at it. I'm also, when in my spare time, which is not very much, working on some other projects. Like I've got one over here this is just beginning, but I'm trying to interface a modern microcontroller, an ARM 32-bit processor, to an old style serial communications chip from dating back from the late 80s or the 80s or so. So I've got all the parts here, and in a little bit I'm going to start wiring them together, and then I got to write the program for the ARM chip to talk to this old style serial communications chip. And then I've got an Ethernet port over here. So the idea is basically to glue together this old style serial interface, the kind that would talk to a modem or another computer over a serial interface, but bridge it to the Ethernet interface so the modern computers can talk to these old peripherals. So that's a little project that I'm working on separately outside the course. Oh, I've always wanted to get one of like those old TTYs. I would have no idea where to store it, but it'd be nice to actually get a hold of a real one, open it up, and then show you how it actually works. But they're big. They're big and bulky and noisy, and my wife would probably say, get rid of that thing. If you're lucky enough to live in a large city, there may be like an old computer museum you can go to and see these things. Like in the Bay Area, in the San Francisco Bay Area, there's the, I think it's called the Computer Museum. You can go there and you can see some of these old computers from the 40s and the 50s and the 60s and the 70s, and most of them are working. So they've got them turned on and you can actually sit down and use them. I've been to that museum, I think, once. It was really cool. And that was about 10 years ago, so it's probably changed since then. Probably got more stuff. Okay, I think that's about it for today. So I hope you all have a great rest of the day. I will see you for this course next Tuesday. And then if you want to also poke your head in on the discrete structures course, then you can do that on Monday and Wednesday, same time. All right, so I think that's it. We're done. Take care. Have a great day. I got to go and do some work and then go pick up the kids from school. Yes, virtual terminals are still called TTYs in Linux. Yep. TTY stands for teletype. Yeah, so you'll see in your Linux system, you go into a directory called the device directory. You'll see all these listings for virtual teletypes. So it's still, to this day, believes that there are teletypes physically connected to the back of it, even though that's not the case anymore. But you could. On your PC, you probably have a couple of serial ports. If you have a legacy PC, you could actually plug one of these old style terminals into one of those serial ports, and it would probably just fire right up and display a login prompt. That's kind of like my dream. If I ever had one of these old teletypes, or even a simulation of one, not a simulation, but like a, if I could get like a smaller version of one, you know, something that would, oh, I know maybe what I could do is, you can't see it, but I've got an old laptop up there, a really old one. All it has is basically a screen and a keyboard. It's got a processor and it can run programs, but I could put it into a mode where it just simply displays anything coming over the serial line, and anything you type goes back out of the serial line. And then I could connect that up to an old like legacy PC that has a serial port on it, and we could just get the two of them talking to each other. It wouldn't make a big loud clattering noise like an old TTY would, but at least it would display the login prompt and I could log in. Maybe I'll try that one of these days, just see if that works. All right, you too. Have a good one. Take care. Have a great weekend. Even though it's Thursday, it's the start of the weekend for me and my students, and I will see you next week. Okay? All right, bye-bye.